All right, guys, now it's time to talk to you about the trick. The trick is how to manipulate this equation one more time in order for us to solve it easily, somewhat, and get a number without using Excel and linear regression lines and all of that mess. Okay? So I told you that we were going to focus on this bracket in a final, the final concentration of the sodium after that dilution took place. Well, look up here at the top. Do you see what we did with the standard? We took 5 mils of sodium and we diluted it to a total of 100, right? And we used this dilution equation in order to get to that part. Well, I'm going to use the dilution equation again because, you know, the sample was diluted as well. Well, what does that mean? Okay, well, let's take a look. Whatever the initial concentration of sodium was in the beginning, as it was given to me in the lab, we took 95 milliliters of that sample. 95 mils of whatever that concentration was. So bracket NaI. And we diluted that in a way. We diluted it to a final concentration. Don't know what it was because I didn't know what the initial was. But we know that we diluted it to a total of 100 mils. That's what the directions up here told us, right? We took 5 mils of standard, we took 95 mils of sample, and we mixed it together. So in the first dilution, it was 5 to 100. Well, in this one, it's really 95 to 100. Oh, okay. Maybe you see where I'm going with this now. If I took 95 mils of an unknown concentration and diluted it to 100 mils, I still don't know the concentration of it, right? But I can use a little bit of the math and I can manipulate this around because we do not like these two variables. They're different. Bracket NaI and bracket NaF. I want those to be the same. Well, if bracket NaI is what I want to solve for because that's the initial concentration of the sodium, then I'm going to solve this equation the proper way. I want NaF in terms of NaI. Okay, so what does that mean? Well, if I take this setup, this dilution equation, and I divide by a 100, the 100s cancel, and I am left with NaF on this side, and it tells me your final concentration of sodium is equal to the initial times 95 divided by 100. That's your dilution step. That's all that is. And that's the way that I want you to think of it. Because if you think of it that way, then you can rewrite this equation and you can have it to be solvable, or at least easier. So Na sub I equals 4.27 divided by 7.98. Well, we already calculated that first one, 0.104. And now what I can do is I can go in and rewrite this variable. And I can rewrite it in terms of Na sub I times 95 divided by 100. So this whole thing, because that says equal to NaF, right? That whole thing gets to be replaced into the NaF spot. So now I've got to work my magic a little bit. 95 divided by 100, that's 0.95, right? So I'm going to clean this up. 95 divided by 100 is 0.95. I don't really like fractions within a fraction, right? So I need to get rid of them. So 0.95, I can take those two numbers and divide them into each other. That's no big deal. That's not a problem. So I'm going to go back and I'm going to rewrite this. And now I'm going to put 0.95 times bracket Na sub I. That's all I did. 95 divided by 100. So now this equation only has one variable to solve for, the NAI. That's it. So we need to manipulate this equation around. We need to do a little bit of algebra with it. We need to work through the math in order to solve for that variable. Okay, so I'm going to clear out this screen, make sure you got everything that's on it, and we're going to continue on with this setup. Okay, so now that the screen is cleared, I'm going to simplify this number over here to the right-hand side. 4.27 divided by 7.98. And I'm going to get 0.535 as an answer. All right, so that's the first thing that I'm going to do. 0.535 as an answer. So I still have NA initial on top, which is what I'm always been after. And I haven't touched any of this down here at the bottom. Nothing at all. But there we go, in terms of all NAI. So if I asked you to solve for this equation, solve for the variable, if that was an x on top and this was an x down here at the bottom, the first thing that you would probably tell me would be, get rid of that denominator. Get rid of everything down here on the bottom, and that's true. We need to multiply both sides of the equation by what's on the bottom. So I need to multiply this 0.535 by 0.104 plus 0.95 times bracket NAI. So this cancels, and I am left with NAI equals this garbage over here to the right-hand side. Now, how do we solve that in algebra form? Well, this is called the distributive property. So I'll take this number, multiply by that one, and then I take that number and I multiply by this one. So that goes to every single thing on the inside. Now, keep in mind that this stays together. Those are not separate terms, okay? So NA sub I equals, I'm going to do the first one. I'll get a full-blown number here. 0.535 times 0.104. I hit enter, and I get 0.05564. Plus. Well, I got to do it to the 0.95 as well. So I'll bring the calculator back up. 0.535 times 0.95 equals 0.5083. And that still has a bracket NA sub I after it. Okay, so we're getting closer, right? We're getting closer to solve for the variable. Well, I have to understand a couple of things about basic algebra here. Number one is that there is a 1 that's understood to be there in front of that NA sub I. If there's no constant written, it's understood to be a 1. So to solve for x, which is NA sub I, I've got to get these terms on the same side of the equation. So I'm going to subtract 0.5083 bracket NAI from each side. So 1 minus 0.5083. Well, if you really need the calculator for that, that's okay. I'll still go through the motions. 1 minus 0.5083 equals 0.4917. So 0.4917 bracket NI. That's my variable. That's what I want to solve for. And now to solve for x in a normal equation. This is 0.4917 times x. So we're going to divide each side of the equation by that number. So bracket NAI, which is what I was always after, is equal to 0.05564 divided by 0.4917, and I hit enter, and I get 0.113 as an answer. There you go, ladies and gentlemen. That's how you solve a standard addition problem using no graph. We had a sample that was given to us. We ran it. We made one addition, and we ran it. And using that ratio, we were able to calculate the concentration in the unknown when it was given to us. 0.113. Now, the 0.113, that is the concentration that was given in the problem, and that concentration is going to be in molarity, right? The signals were in millivolts. Those canceled out anyway. Who cares about those? But notice the concentration was 5 mils of a 2.08 molarity. So that means that this concentration is going to be a molarity as well. They have to match. So there's the trick, people. I think that you're okay understanding that this is the variable that you always need to solve for. I think you're okay with the signals over here to the right-hand side and where they come from. I also think that you're probably okay with how we got the 0.104 in the previous video. That was just a simple dilution. It was what we've always done. Take the standard that you've added, take the concentration of it, take it to the line, use the dilution equation. What was it that you added? It was maybe this piece that was a little bit new. But here's the thing. Look at what happened. We took 95 mils and we took it to 100. 95 divided by 100 is 0.95. That's the way this thing is going to look all the time, right? So, for instance, if I had 20 milliliters of sample and I took it to 25 mils in total, well, if I wanted in terms of the NAI like I did up here, or whatever I'm looking for, just take that ratio difference. 20 divided by 25, 0.8. So 0.8 would go there instead of 0.95. That's all that you got to do. The only thing that I did is kind of explain to you where that number was coming from. So take the amount of sample that you used in the prep, divided by the total volume that it got to, and divide those two numbers. You're going to get the proper decimal that will go in front of there every single time. And that's all that you need from that point on. Everything else is a little bit of algebra work. Making the equation look the same on each side, getting the groupings together where they need to go. That is basically a math course from that point on. But how to get the number, that is where that number comes from. All right, so we're going to do one more example of standard addition without using a graph. And that's going to happen in the next video. And hopefully you're going to see that it will go much quicker. I won't babble and talk about where these numbers are coming from as much. We'll just look at an example problem. We'll start cranking things out by hand. And you're going to see, hopefully, these things will become much, much easier. And you might prefer them over the Excel version.